Now it should be working, yes. All right. All right, thanks Václav for the invitation. It's great to be here. Last time was a few years ago now that I visited Václav at UTIA. And yes, so I'm working in this place, in this Department of Data Science at EURECOM. EURECOM is a research institute and graduate school in the south of France, close to Nice and close to the border with Italy. We welcome people to come and visit us whenever there is scientific interest, let's say, not just coming to go to the beach, right? But so yeah, today I'll be talking about Bayesian deep learning. So my talk would be rather introductory, I would say. I will tell you a little bit about a few directions that we've been identifying in the last few years that we think are kind of interesting to work on. And so I'll start with some motivation, and then I'll be talking about brief introduction to Bayesian deep learning, and then some things that I'm quite excited about and some ongoing work. So the main motivation is decision making. Ultimately, as people that handle data, what we want to do is to be able to do assist the process of decision making, because this can be very helpful for policy making, for the environment, for example. Think about climate change, how much money is poured into policies to counter global warming, for example. So is there really global warming or not? So these are the kind of questions that as people that work in machine learning and data science, statistics, environmental sciences, we should be able to address. Healthcare, you know, how important it is to find good strategies for treatments for people. Society, you know, should we give or not credit to someone based on their history and so on. So all these things are actually happening these days. You know, we're using data to actually make decisions at these levels. And so, as a reminder, I take this book by Norvig and Russell, the artificial intelligence book, where there is a nice explanation of what AI is, because people talk a lot about AI in the news. You know, we should remind ourselves that we have always something that is related to probabilistic reasoning and utility theory. So we cannot make good decisions if we don't know how to associate some sort of utility or cost to various decisions that we can take. And the probabilistic reasoning aspect is allowing us to really weigh these possibilities of things happening in a proper way. And so both these two pillars really form what we call decision theory. And in this talk, I will be focusing a lot on what probabilistic reasoning is and the importance of this in the context of models that we work with these days. And for me, most of the things that we do in machine learning is actually estimating functions. So I could go around and say that my job really is estimating functions. And so here I have two examples. One is a regression problem, one is a classification problem. In the regression problem here, I drew a function black here, and then around that I generated some noisy observations. And on the right here, I have a classification problem in one dimension. So I have one feature here. And for, again, I drew some sort of random function, which is between 0 and 1. And the classes are then realizations with probability given by this function here at any inputs. So our job as people working in machine learning is to try to reverse engineer this process and try to get a distribution over functions after looking at this data. And interestingly, a lot of problems can be cast this way. So really, being able doing good function estimation is really something very important. And so these days, neural networks, people talk about them everywhere, even in the news these days. So as someone that has worked traditionally on shallow models like Gaussian processes and kernel methods, it's been interesting to actually dive into neural networks more as a way to sort of maybe combine the strengths of probabilistic modeling using Gaussian processes with neural networks, as I will be talking about today. And so what deep neural networks do, and why are they so successful? Well, in practice, what they do is to implement some sort of, sorry, wrong button. They implement some sort of composition of functions. So At each layer, we take the input here. So this is not a graphical model. This is just a diagrammatic representation of what a neural network does. You take some inputs, multiply some weights, apply some nonlinearities, and then you keep doing the same operations again and again. So in practice, this is implementing some sort of composition of functions. And this is why it's really hard to do any theory with the deep learning, because compositions are really hard to study mathematically. And the parameters of these models, as you can see, enter in each of these functions in the composition. So really, optimization, theory, these are all things that are quite hard to do with these models. Nevertheless, they're really powerful because they combine small, simple things, and the composition really can make something, the combination of small and simple elements into something which is very complicated in the end. And so we say that the capacity of these models is really large because we can really represent a really large class of functions. And so if you actually do this, so what you would do is to try to do some sort of optimization of your parameters by minimizing some sort of loss here. That could be the distance between your labels, so the y-axis, the y values here, and what your function is producing, what your model is producing, which I denote by f of xi, and then some regularization can be implemented with L2 normalization, L2 regularization, or early stopping, dropout. So there can be many ways in which you can implement some sort of form of regularization. And so if you do it, this is the kind of picture you get. You get some sort of functions that kind of fits your data. Nothing too complicated. But if you try to use these for applications that are risk sensitive, then you have a problem. Why? Because these neural networks, as you have seen in the picture before, they just give you a point estimate for your predictions. And so what happens is that they can be overconfident sometimes in predictions. So this is a famous example of when things went wrong with the Tesla Model S, for example, that was not able, the vision system was not able to recognize that in front there was a truck, and so the car just drove through and killed the passenger. And so this was a very big deal in the news, and kind of points to this problem of overconfidence of these models. There was also a similar accident that happened with Uber. They were testing self-driving car software, and they were trying it, at night with the low lighting conditions. And again, the vision system failed to identify someone going by with a bike. Other things that happened in the news also, some racial group that was identified as gorillas from the image Google Photos labeling software. And so all these issues point to the fact that somehow, more and more we are relying, we will be relying on this software, but really the overconfidence is something that is really problematic, and we haven't made enough progress in this direction yet. So maybe a bit more light topic. There is this interesting Instagram profile. I think it's either Instagram or Twitter, I forgot. Now, one of the two. And so what this guy does is to use this ResNet architecture, and he feeds random images to this thing, and then he posts the results that he gets from this ResNet. And so you see that, for example, this picture gets 99.99% confidence that this is a picture showing ping pong balls, right? So there is also this one, which is quite funny, pineapple here, which is. So all these, again, I mean, this is a bit more light weight compared to what I showed before. But again, imagine that these get routinely employed in decision-making pipelines. So this is obviously very catastrophic. And so how can we equip deep learning models with the ability of reasoning about uncertainty, and where we can actually trust this level of confidence here? And so, so the way we're going to do this is to do it through Bayesian techniques, because we can express everything in terms of probabilities, and this is a really nice way to communicate uncertainty. And so if we think about the quadratic loss that we had before, for example, so what we can do is to just exponentiate the negative loss, and we get something that looks like a Gaussian. And so now, instead of thinking about minimizing the loss, we can think about maximizing the likelihood, okay? Which is this probability of data given parameters and inputs, okay? So this is the equivalence between the two. And so now, the nice thing about this is that if we armed with this equivalence, if we just optimize, we don't change anything. Minimizing the loss, optimizing the likelihood is the same thing. But now, if we have access to this function, which is the likelihood of data given parameters, now what we can do is to put a prior over the parameters and do something magic, which is obtaining a so-called posterior over the parameters. And the way it works is that if we have a vague idea of what the parameters of the model should look like, in light of observing data now, thanks to Bayes' theorem, we use the conditional probability of y, our labels, given parameters, and we can actually invert it to obtain the probability of our parameters given the labels and the inputs. And so the way it works in a cartoon fashion is that we have a vague idea of what the parameters look like, and conditional observing data, we have now a new distribution of values of W that are compatible with the data that we observe. And this is quite nice, and it's quite easy to actually write it down. The problem is that in order for this distribution over the parameters to be a proper distribution, we have to normalize it. And this normalization requires us to solve an integral which is as large as the number of, as many dimensions as the number of parameters. And so if you have these models now that have hundreds of millions of parameters, billions of parameters, we have to somehow solve integrals in these billions of dimensions, or try to use techniques that avoid actually to compute these approximations and so on. And so this is really, well, all the business of approximate Bayesian computations that I will briefly touch upon in this talk. But really, I mean, this is a very general, very simple way of thinking about the way Bayesian inference works. The magic of this is that now when we make predictions, and so if you're not Bayesian, I encourage you to think about it, because the magic of this is that now when we want to make a prediction for a new test point, input x star, we can get the distribution over y star, so a predictive distribution, which now does not depend on parameters anymore, because we can actually integrate them out. So we actually make a prediction with our model, and we weight all these predictions by the posterior. And if we do this, we obtain something that in the left-hand side does not have parameters anymore. So it's a parameter-free prediction. So philosophically, it's really nice. Except that it's actually parameter full, not parameter free, because actually we're accounting for an infinite number of parameters that are compatible with the data that we observe. And this is really nice. So the predictions that you have in the case of regression and classification would look something like this. It's quite nice because now we want to make a prediction and we want to communicate a prediction. We can communicate not just one value, but we communicate a whole distribution of values that are compatible with the data that we have observed. All right, so this is quite philosophically quite nice, and this is a really nice way I like to think about when I do function estimation. So I wanted to maybe briefly talk about the timeline of Bayesian deep learning. So people have been talking about being Bayesian about deep nets since the 90s already. So David Mackay has a very nice work in 1992 already. So we're talking about 30 years ago. And quite important works also in the connections of deep nets as Gaussian processes, actually shallow nets as Gaussian processes, where you can view a shallow neural network, a Gaussian process as a shallow neural network with an infinite number of neurons. So this connection was already investigated by Radford Neal in 1996. And since then, not much happened until we had this explosion of deep learning where people were optimizing these huge models using mini batches, stochastic optimization. And so people started thinking, well, maybe we can do some sort of stochastic version of variational inference, which is a way to do approximate inference for deep nets. And so this was in Graves 2011. And also people started thinking about maybe Markov chain Monte Carlo sampling to actually draw samples from the posterior distribution over parameters, again, using mini batches, and this is 2014 already. But actually something that changed the game really was TensorFlow, because, I see a lot of young people here, but before 2016, we had to compute gradients by hand, write down gradients by hand, and then implement them, debug them, make sure that they were right. And now all this is completely offloaded to automatic differentiation. Automatic differentiation has been out there since forever, but really implemented in a powerful way in TensorFlow was something quite recent. And now all the implementations of approximate Bayesian inference for these deep nets now rely a lot on this automatic differentiation. So we have really the possibility to do experimenting of a lot of ideas quite in a fast-paced manner. Also, there was this nice work in 2016 of dropout as variational inference, or a connection between dropout and optimization as a form of degenerate variational inference, I would say. So this was 2016, and also and I would say that this was really the first. So if you want to do some sort of Bayesian convolutional neural network where you're probabilistic about all the filters in your convolutional neural network, this is really like one very practical way of doing it, and it kind of works. Okay, so before that, we could not find a single implementation of a Bayesian convolutional neural network, even approximate. And so we spent a lot of time with my colleagues. I got an email at some point from one of my colleagues at Columbia. He told me, I cannot believe that there is not a single paper before 2016 that does that. And actually, we couldn't find any. And one of the reasons why, and it's something that I'll be talking about later, is also that there is an issue with the way we choose the priors for these models. But I will be talking about that in a second. And also the first workshop on Bayesian deep learning at NeurIPS 2016. That's, and so why don't people use Bayesian deep learning? I mean, it sounds so good. You know, it should work as well as, you know, be flexible as any deep learning models because it's just the same models. And plus, we have this additional benefit of having the possibility to get distributions in the output and do good uncertainty quantification, good confidence estimation. Well, if you talk to a lot of people that are not Bayesian, or maybe you are not Bayesian and you're thinking, well, it's too slow. I mean, I would never do this Markov chain Monte Carlo stuff or approximations of my posteriors because it's just slow. And actually, I mean, if you are optimizing neural networks these days, that's also not very fast. So yeah, you need GPUs, you need to run them for days and so on. So actually, doing this Markov chain Monte Carlo that we do is not very slow compared to that. Maybe we need a few more iterations, a few more parallel chains, check convergence of the chains and so on. And also, not very difficult to implement anymore because also optimization. Sometimes you have to come up with a schedule for learning rates, which are difficult to come up with. You know, sometimes you read papers where they've done a crazy learning changing of the learning rates schedule over time, and it's very difficult to understand. And actually, we have similar problems in sampling with Markov chain Monte Carlo, but actually these are common problems between the two, optimization or Markov chain Monte Carlo. So I wouldn't say that that's the problem. But yes. Yeah. You're right that you're in a large dimensional space usually, and the problem is that the landscape of optimization also will require you to do a lot of iterations before you actually converge to something relatively good, and so you have to run this optimization, stochastic optimization for a very long time. With stochastic Markov chain Monte Carlo, the advantage is that there are lots of so even in optimization, you can kind of exploit that. But in Markov chain Monte Carlo, the exploration of the space is facilitated by the fact that you have a lot of redundancies in the space. So if you permute the order of the nodes, for example, you get the same output, if you permute in a certain way. And so this creates a lot of modes in the parameter space, which are actually giving you the same output, okay? So when you do the exploration of the space, you actually capture a lot of these configurations automatically somehow. So the sampling is sort of facilitated by that. And it's not more expensive to sort of explore that large dimensional parameter space than actually optimizing a function in that large dimension. At least that's our experience. We do convergence tests, and we see that actually the Markov chain means. Yeah. Yeah. all right? But there is another problem, that performance is not good. So if you try this Graves 2011, so you do your nice implementation of this, 2011 now with TensorFlow, PyTorch, whatever you want, you run it, you get performance which are terrible. And so some people started saying, well, maybe Bayes is not optimal. And this is sacrilegious, obviously, because Bayes theorem, there's nothing wrong with Bayes theorem. It's just what the ingredients you put in Bayes theorem. And so people started, wrote a lot of things that are along these lines of saying, well, we should propose different things, tempering approaches and so on. And these all point to the fact that the choice of we also did some work trying to improve variational inference, better optimization. We were just chatting before about this. But actually the problem was that really choosing sensible priors is a problem that has been overlooked a lot. So usually when you don't know about some parameters, what do you say? Well, we just put a standard normal and off we go. But actually doing this is very detrimental to when you do it for models that have millions or hundreds of millions of parameters. And actually specifying good priors is not that easy. Why? Because reasoning about what is the effect of the choice of these priors into the output is really hard. And why? Again, because the complexity of these models is very large, and we have these compositions of functions which makes everything very, very hard. And so these priors of convenience that people would say, yeah, you use some sort of standard normal prior or some sort of Xavier initialization kind of prior where you have 1 over the cardinality of the number of neurons connecting to a neuron and so on. All of these are terrible choices, really. And so, this animation works. And so this is just to give you an example of what the kind of functions you're representing when this is like a 4-layer fully connected neural network. And so what happens here is that I'm changing the prior standard, the standard deviation of the prior of the weights, the top slider, and the bottom one is where you have this bias that also adds to the computation of the function at each layer. And you see that the effect that these guys have in the functions that you get in the output is very strange. And somehow all these functions look kind of pathological. So if you have some interesting data that does something that where some oscillations and things, you would never choose a prior like this. This prior doesn't look like it's doing much anything sensible in the output, right? So these functions look a bit pathological. So what can we do to actually do things better? Well, some of you know me, we worked a lot with Gaussian processes. And why? Well, because Gaussian processes are good priors over functions. Good in the sense that we understand what kind of functions we're implementing. So we have a kernel, a covariance function that has parameters. So here I have this alpha parameter and this length scale parameter, and their interpretation is very nice. So I know that the length scale parameter is going to give me some sort of characteristic length scale for the functions I can draw from this prior, which is the effect that you see now. Long length scale gives me functions that are have characteristic long length scales which are very large. And now also this other parameter alpha is telling me what kind of marginal variance I want for the output. So it's kind of passed me the term in more interpretable way of specifying a prior over functions compared to Bayesian deep neural network. So what's the idea? Why don't we try to impose these functional priors to Bayesian neural networks? So the idea would be to try to change, also tune, if you like, the priors of the Bayesian neural network so that in the output we would get things that look like this. And so we would sort of merge the convenience of specifying sensible priors in the functional space with the flexibility of neural networks that implement these very complicated compositions of functions. And so this is really the simple idea that we have and that we try to implement in a sensible way. And so now the problem is the following, that for the neural network, we don't know what is the distribution of the functions that we get. We only can sample from this. When we sample from a distribution over the weights, we get some sort of functions in the output. So we can get samples from this distribution over neural network functions. Whereas for Gaussian processes, we have a closed form. We know that the Gaussian process gives us a joint Gaussian. So how do we kind of match these two? So the first thing that you may think is to kind of minimize some sort of KL divergence, because this is what, when you have distributions, you try to do that. Except that for Bayesian neural networks, we only have samples. And so if you actually expand the KL between these two distributions, you get something which is an entropy term here, which is not very nice to estimate just by sampling. So the variance of this is very large and it's very unstable. So what we actually did was to actually use a different way of computing this distance using the Wasserstein distance. And Wasserstein distance has got like a funny form. So it's a difference of two. So if we're trying to compute the distance between two distributions, so what we do is to compute this distance as the difference between two expectations under the two distributions. And in the argument, we have this phi of x, where you can think of this phi of x as something that's trying to maximally distinguish the characteristics of the two distributions. So it's some sort of adversarial kind of problem. So you're trying to find a phi that maximally makes the samples from p and nu maximally different, if you like. Okay? So we have a supremum operation under this function phi that is actually one Lipschitz of this difference of two expectations. Okay? So it looks complicated, but actually because it's expectations, we do Monte Carlo estimates of these, and then this becomes kind of nice to compute. And the other thing is that then we don't need to know the closed form for these two distributions. We just have to be able to sample from them, because then we estimate these expectations using sampling. And then how can we implement? So this is a kind of a funny way of computing an objective, because we have to maximize with respect to phi, right? Yes.
Sorry, I got a bit lost. So you started with the fact that you want prior predictive to look like a Gaussian process?
Yes.
But now we should be talking about how to get the priors of the parameters so that the prior predictive
Yes.
looks like a Gaussian process.
Exactly.
So where did we get the samples?
So
this looks like learning.
yeah. So okay, I'll give you the storyline again. So this is just a way. How do we actually compute the distance between two distributions?
Yeah, but you say that one of the distributions.
And now one of the two will be parameterized. Will be a function of how we choose the priors. And so now this is just to compute the objective, and now we will have to minimize this with respect to parameters of the neural network, of the priors over the parameters of the neural network. Does that make sense?
Yeah, but then we should have them analytically, right? Because we're taking them as priors over the parameters that we will then sample as.
No, it's not going to be analytic, because so this objective is a fairly complicated object that it depends on samples that you get from the neural network and the Gaussian process in our case. Yeah? And the samples depend on how you chose the priors for the neural network. So in the end, this is just the objective, how we actually compute the objective. So we have to do a maximization, if you like, over the space of all this one Lipschitz. But then we have to minimize this objective with respect to the parameters of the priors over the weights of the neural network.
I think it's going to be just like part of the objective.
Yes.
Which ensures that like the prior is, I think, Gaussian, and then you will have some additional term which like maximizes accuracy.
But it's as simple as now minimizing this with respect to any parameter of pi, really.
Okay, so maybe just.
Yes.
So this is about choosing the right priors, or is this about learning the network?
This is about optimizing priors, which sounds very weird, because priors you should never optimize. But here we're trying to find the priors for the neural network such that the outputs that we get match what the Gaussian process would give us of our choice. So we have an ideal Gaussian process that we think is a good prior for our problem. And now we say, okay, now let's tune our priors so that in the output we get something that looks like a Gaussian process. I have pictures, so that maybe that helps. Yeah? And so you see, like, there is in order to compute the objective, we have to solve a maximization problem with respect to this phi. And so this phi, if you implement with a neural network, it becomes a simple optimization problem you can do with mini batches and so on. But now what we want, yeah, okay. So let me just go back here. So yeah, so here I'm just repeating the fact that I don't need to know the density here. I just need to be able to sample, and yeah, all the expectations are computed with Monte Carlo estimates, so it's all easy and sample based. And so here the picture is that my optimization is going to try to make samples look like my target GP prior. So if I have a GP prior that I like, and I think this is a good prior for me for my problem, then the optimization, as it goes along, is going to try to produce samples that look like the ones from a GP prior, okay? And so it's a min-max problem because we have an internal way of computing the objective and then an outer loop of minimizing this objective with respect to the parameters of the priors over the parameters, okay? And so these are the kind of samples you get. You see, they're not perfect, but it's something that starts to look like the prior we have. And so if you compare with what you had at the beginning of the optimization where the functions were all flat, we get something which is a bit more interesting. And if we do it, so these are a few examples. So if we have neural networks with fixed Gaussian priors or fixed normalizing flow priors, because we also can do now crazy priors if we want to make the expressivity of my prior larger. So I can do also normalizing flow priors, which people use normalizing flows to actually get approximation to the posterior. But now if we do it, then when we optimize these priors, we get something that starts to look a bit like the GP prior, except that you see that if you have something which is not very flexible, like just a simple Gaussian prior for each weight, and we have rectified linear unit activations, obviously, I mean, if we have something which is infinitely differentiable, we cannot match perfectly, you see, and you see that you get samples that are okay-ish, but not very good. And you see that the Wasserstein optimization objective gives you something that goes, gets lower and lower, but never reaches zero, except if we do normalizing flow, we have more flexibility, so we can actually match quite nicely the GP prior. And so now if we use this in a toy example, the kind of Gaussian process posterior we like usually because we get these nice confidence intervals away from data that we really like when we want to communicate results, when we want to know when we don't know. And if we use these priors which are fixed, you get very low uncertainties everywhere. So this is not very good at capturing uncertainties. Whereas, if we do it with this learning, optimization of the prior, if you like, then we get results which are much nicer. Okay, so this is one toy example to illustrate the fact that we get nice certain quantification. Now, the good thing about this is that also we have this big table of results. We have millions of results in this paper where we actually show that also in terms of performance now, by using these priors, we get performance that are quite nice. These are all obtained without data augmentation. So if you're working with CIFAR 10 and you say, well, state of the art is 99% accuracy, it's because they do data augmentation. We don't do any data augmentation. We wanted to just separate the effects and just show that, doing this sort of optimization of the prior, you get massive improvements compared to other things that people have tried to do before. Different architectures, different number of parameters. So AlexNet, I think we have, so VGG, I don't remember, we have one of these two has a few millions of parameters. Good question. I would have to check with my PhD student for that. No, it takes, it's like optimizing these networks. It would take a fairly reasonable amount of time to do it. Okay, so now we can go crazy, because now what we can do is to actually do autoencoders. You know, now we did it for supervised learning. Why don't we do it actually for unsupervised learning? And now the common trend is for people to actually do something that is variation autoencoders, where they actually put a distribution over the latent space, and they do this neural network in a configuration where you have inputs that get into a latent space, and the latent space gets funneled back into the original input space. And so somehow you're trying to learn some sort of identity with a bottleneck in between. But again, these neural networks, you can try to maybe treat them in a Bayesian way instead of having a variation formulation. And that's exactly what we did. And I'm gonna maybe, spend a bit of time just saying that if you do variation autoencoders, you're bound to use variational techniques, which are approximate. They use a lower bound. Obviously, or if we do Markov chain Monte Carlo, we're also doing something approximate, but at least we're targeting the true posterior instead of relying on a variational lower bound. And so in practice, the only problem is that then we lack generative modeling, because now we don't have a distribution directly on the latent space, but we have only randomness in the latent space, which is due to the randomness in the weights, right? And so, but this is kind of easily bypassed by just doing some sort of mixture modeling in the latent space once you have trained your model. And actually, if we do it, this is the picture I like to put everywhere, every time I talk about this, is that if you have a small data set, this is really where things get wrong for a lot of these models. So these are all these variations on variational autoencoders. There is a Wasserstein autoencoder, beta vi, variational autoencoders with fancy priors on the latents and so on. And so you see that the reconstruction is terrible for all of them, and actually the generated samples are even more terrible. Except that when we use this optimization of the prior, you see that the faces look much better. And even compared to GANs, which are really state-of-the-art for these kind of problems, because of the size of the data sets, which is very small, you get faces which are completely messed up. And so this is, again, a good indication that being Bayesian and doing things right should give you better results in general, which is consistent with my understanding of Bayesian principles. All right, so what I just wanted to conclude maybe briefly with a few things that I'm quite excited about. Combining all this Bayesian deep learning business with physics is something that I'm quite excited about. So we did some work on differential equation models back in 2018, and something that came out, also this we did in 2018, but it came out this year in Bayesian analysis, where we try to combine Bayesian deep learning, Bayesian deep Gaussian processes, or Bayesian deep neural networks in general with physics. And so emulation techniques, how you implement emulation techniques for parts of the code maybe. I'm quite interested in thinking about this work I presented today as thinking about maybe neural networks that are informed in the way they generate functions based on the physics, so kind of physics-informed priors, if you like, using the framework I presented today. But actually, there are some identifiability issues when using some of these frameworks for combining physics and deep learning, so I think there's a lot of work to be done there. So I'm quite excited about this. Some work that actually 2 days ago was accepted at ICML. What if you want to put some latent representation, structural representation in your latent space? So for example, you want, you know that your data evolves over time, so maybe your latent space should have some sort of temporal, should be a temporal process, maybe a Gaussian process. And the problem is that when you have an encoder, the encoder would determine the prior that you have over Z by the prior that you have over the encoder. And so here, we found a way to actually merge, having still a fully Bayesian treatment where we actually impose a certain prior over the latent space. And so this is kind of nice. We can do sort of compression of videos using these Bayesian autoencoders and things like that. Other things I'm quite excited about, maybe extending all these Bayesian autoencoders to what other people have done in variational autoencoders, where you start having modules for doing interpretability or causality and so on. So this is all stuff that I think could be kind of nice to do. This is also like a random orthogonal direction we worked on for some time with trying to use some optical hardware actually to do faster computations with the lower power consumption. So how to actually use this particular hardware that does a very particular computation. So you give an input X to this hardware, and it spits out something which is a random rotation of the X vector with a nonlinearity, which is an operation that is kind of useful for doing some approximations of Gaussian processes, for example. But how can we use this beyond Gaussian processes for deep neural networks and Bayesian neural networks? Anyway, so yes. Some applications where I would like to get more involved with environmental sustainability in life sciences. We've done some work on Alzheimer, for example, with life sciences, well, with colleagues in institutes in life sciences in various institutes, King's College and Donders Institute in the Netherlands, but I would like to do more. But so this is just to give you also a brief overview of the kind of activities in case you're very interested, coming and visit us and kind of get exposed to this. And with this, I think I thank you for your attention.
Thank you very much for your talk. I was asked to record the questions on the microphone. So if anyone has a question, I will bring him a microphone.
Okay. Hello. Thank you for the talk.
Thanks.
And I would like to know, like you defined like the prior over weights, whether you also tried to create a prior over architectures of the neural networks, like number of layers.
That's a great question. So at the moment, we have not. So we are not putting a prior over the number of layers, for example, or number of neurons. I think one of the issues with these ways of thinking is that then you would have to deal with the Markov chain Monte Carlo approaches that go to different dimensions, and generally this is really hard to do. It's possible to do, like with these reversible jumps, for example, Markov chain Monte Carlo. Generally quite awkward to implement, I think. One way that I think about these issues of choosing an architecture then is, because now we can do Markov chain Monte Carlo sampling, then we could use techniques to do marginal likelihood estimation, which would be quite good. Marginal likelihood estimation, which is the kind of quantity that we need to do model selection. So then the idea would be then you have maybe 10 different architectures that you are not sure which one you would like to pick. And you would run this sort of very expensive estimation of this marginal likelihood, but now feasible because we have these samplers that work quite nicely. And then compare these marginal likelihoods and then pick the best model, for example, or weighting multiple models, for example. That would be possible too. Yeah, why not? Yes, it's absolutely, yeah. I think it's heavily underexplored as a field. So the one of model selection using Bayesian principles, because just people have never really dared to do marginal likelihood estimation. And so we did something with lower bounds. So if you have smaller architecture where variational inference kind of works, then you can use the evidence, the marginal likelihood lower bound, the ALBO, the evidence lower bound, as a proxy to the marginal likelihood. And so you use that to do model selection. But some people have obviously warned against the use of this because this is just a lower bound. So it's possible that your bound is so loose that it's not very meaningful to actually compare lower bounds only. So I think, yeah, I think it's still very underexplored. So it's a great question. And I think it would be much easier to do that as opposed to do sampling where you have dimensions that change and number of neurons that change, number of layers. It's, yeah, that would be pretty painful to implement.
So you said that in terms of time for the computation, it doesn't take so much compared to regular training, but I imagine that when you're sampling a neural network, you're sampling it in a very, very large space.
Yes.
So in terms of memory, that must be very, very hard to do. So how many samples do you need to properly estimate a network, for example?
Good question. So in order to check convergence, also there is this other issue that in order to check convergence, we do multiple chains. So that also adds to the whole burden of computing. And also that when you want to do predictions using this equation, there you go. So we sample a bunch of, so we use Markov chain Monte Carlo, and then we have to store few configurations of, yes, this doesn't really work, but a few, yeah, when we sample from this guy here, in the end we have to save, let's say 100 samples from this that we use to do the average. So in terms of memory also, it's not very convenient to do it. Well, I mean, it's a Monte Carlo estimator, so in the end, well, the thing is that in the end, you see, like this is boils down to something which is much lower dimensional. So you're right that this lives in a very large dimensional space, but because we're averaging things that are low dimensional, then we have this advantage that actually we don't need millions, in order to get low variance estimators. And so that's one of the things. And also the check of convergence of the Markov chains does not happen in the W parameter space, but actually happens in this space. And the reason is that what I was talking about before is that you have a lot of multiple, well, not infinite, but factorially many modes in the parameter space that represent the same thing. And if your Markov chain Monte Carlo algorithm jumps between the modes, in the parameter space, it looks like it's a terrible mixing because you're not exploring the whole space. Obviously, it's a huge dimensional space. But as long as the predictions say the same thing, then this is a really more reliable way of assessing convergence of these samplers. And that's the way we do it. Yes, of course, yeah, you have always the burn-in phase. Yes, absolutely.
So this all happens, you're bypassing the parameter space basically through looking at the predictive.
Yeah, but we still sample in the W space. But yeah, I mean, a lot of these statistics then boils down to actually looking at what happens for the predictions, yeah. Thanks, guys. Thank you so much.
Nice talk, and looking forward to seeing you sometime again.
Thanks. I was also on time. That's great.